So, after this moving bed, we come to the lower part of the blast furnace here, and you can see this is a cohesive zone which we have already discussed previously at many times, and in this region mostly the coke is the solid one, all other thing is in liquid form. So, liquid iron and slag is trickling down through this coke bed matrix. Gas is going up, here is a cross flow and then going counterclockwise. So, gases are rising up in the vertical direction, and because the coke is getting consumed here. So, the whole burden is descending down. So, and because you inject PCI, pulverized coal injection, through the TUR. So, you are having really a 4 phase liquid, fine, gas and solid, which are in the motion, and that is why we call that one as a 4 phase flow. So, in that way this is a quite complex region. So, stability of this region is at most important in terms of getting the efficiency of the blast furnace and smooth operation. This movie will give you some idea about this 4 phase flow. Of course, in this one you would be having a liquid, gas and fines in the experimental condition at room temperature, and coke particle actually are these which are not moving. So, you can see that there is a sort of a flooding is occurring here. So, gas is coming from this side, and this is fines is coming from the top. Fines are deposited, blocking the pores and forcing liquid to build up, and then the flooding and bubbling has started in this. It is a classical example which we talked before about the flooding and loading things. So, you can see in this one how the loading and flooding is occurring in this. In this case, the solid movement is not there, is stationary. So, this is resembling the lower part of the blast furnace, and deposition of the fine one can see even at the top, but liquid accumulation is notwithstanding. In this figure now we will describe about the 4 phase flow, how does it occur. So, this y axis shows the pressure drop and the x axis shows the time, and it is in the 4 phase flow. So, the first one is showing a static bed. So, in the static bed the pressure is delta P1, and after a time sometimes you start moving the bed. So, particles you put them into the motion. So, bed is in motion. So, under those condition your pressure drop actually decreases, and this is quite true because as we have seen before in one of the slide, that in the moving bed the void fraction is more than the static bed. So, this is the condition when gas is flowing and there is no movement of the particle inside the bed. In this condition the gas is flowing, but there is a movement of the particle. So, solid is in motion, and naturally the void fraction has increased, the pressure drop would decrease. And now at this point if we start injecting the fines, so naturally as we had seen before, the fines are going to occupy some spaces between the particle board. So, there would be a less permeability, and naturally the pressure drop will increase, and that is where the pressure drop has increased when we inject the fine. So, gas solid powder flow in this one, and after some time when we inject the liquid, then naturally liquid is also going to occupy quite a bit space, as we had seen in the previous photo videos. So, pressure drop increases further when the liquid flow starts, and that you can see from this figure, and after some time you stop the experiment. So, it comes to 0. So, this is sort of a experimental graph of the pressure drop and how the pressure behaves in various conditions. So, naturally in presence of liquid, the pressure drop is quite high. It is due to the especially due to the maldistribution of gases and fines. So, this is one of the you have seen the video just now, and in that one, if what we have found, if we do not put the liquid from the top, you can see the accumulation of the powder, and between the particles we have talked about this a lot when we were talking about the pressure drop or PCI injection. So, this fine injection or powder injection is representing the PCI, the pulverized coal injection, or any other material, plastic or iron or fines or anything else. So, this occupies the space between the particle, but at few places accumulate in a large quantity. So, opposite wall of the tuya, you can see there is a large accumulation of the powder. So, this essentially what we call the powder holdup. It's like what we had discussed about liquid holdup. So, we had a liquid static holdup and liquid dynamic holdup. In the same way, we have powder static holdup and powder dynamic holdup. So, powder static holdup is the holdup which is in between the particle, the powder which is sitting in between the particle and not going through that. It is just sitting there and it is stationary, and that is the powder which is called the static powder holdup. The dynamic one, just again like a liquid dynamic holdup, the powder which is going along with the gas stream out. So, it is in dynamic position, that is called the dynamic powder holdup. So, we have correlation for dynamic powder holdup and static powder holdup similar to the liquid holdup what we had discussed before. So, we are not going too much into the detail of it. Holdup as such are similar as we had discussed in terms of liquid gas and fine flow. So, one of the correlation which is which gives the static holdup is this, but this static here H s is a static holdup, rho k is the density of the fine particle, G is the mass feed rate of the gas, C5 and C6 are constant, Ug is the superficial gas velocity, and dP is the packing particles size, and this correlation is developed in a cylindrical packed bed system. So, in a cylindrical packed bed system, it is a bit different than a rectangular packed bed system. So, and in this was developed in an ideal condition, and you must remember that in blast furnace conditions are not ideal. When we say ideal condition, so if I look if you look at this, you can assume this one as a cylindrical, but you will see the gas flow and the fine flow is occurring from a small region. and the way this correlation has been developed here, it has assumed the gas flow is occurring uniformly throughout the cross section of it. So, sometimes it is quite difficult to correlate the static fine hold up with this formula equivalent to the blast furnace hold up. In that case, probably this rectangular one may give a better idea, because this has a maldistribution of gas and fine over here. So, this correlation, as I said, is valid only for cylindrical system, and it was developed for the fine glass bead and circular glass sphere. So, packing material is glass spheres and powder is fine glass, and the second one, packing material is glass sphere, but the powder is fine silica alumina. So, based on those experiments, this is done, and these are the value of the constant for these two systems at the feed rate of mass feed rate of gas in this range, and the fine diameter in this range, and particle diameter in this range. So, one should be aware about this condition when using this sort of empirical correlation. Similarly, there is a correlation under the same condition for dynamic hold up. So, it is the dynamic hold up, and kappa is the mass fraction of fines, which is nothing, it is a mass flow rate of fines and gas. So, it is a fraction actually, and C1, C2, C3, C4 are constant, which are given here. dP is the particle size and superficial gas velocity, the void fraction, void fraction of the packing particle, and uz is the minimum linear vertical gas velocity that sustains entrainment of fines, and Re infinity is the Reynolds number, which is given by this formula, where U infinity is the terminal velocity of fine particle. So, and others are constant. So, these all values are given over here. So, using these values under those limit which are mentioned, the condition, operating condition, one can find a reasonable at least the static hold up of the fines and dynamic hold up of the fines, and this can be substituted in the Argon equation when we are making the pressure drop. If you remember, when we did for the liquid hold up the pressure drop, in the Argon equation we subtracted total hold up from the void fraction, and that increased the pressure drop, because it decreases the void fraction. Similarly, in this one, the dynamic hold up and the static hold up of powder can be taken as the total hold up of powder, which can be subtracted from the void fraction, and that will decrease the voidage, and thus will increase the pressure drop in the column. So, one can get a then good idea about the pressure drop in the blast furnace. There is one numerical based on this. So, a pegged wet column of 600 millimeter height and 100 millimeter diameter is filled with 4.65 millimeter pegged particles of glass material. Air is injected from the bottom of pegged bed at a superficial velocity of 0.5 meter per second. Glass fines of 65 micron size are injected at a feed rate of 0.3 kg per meter square second. So, mass flow rate of the fines. The density of fines and terminal velocity are 2500 kg per meter cube and 0.28 meter per second respectively. The porosity of the bed is 0.35. Determine the static and dynamic hold up of fines in the peg bed using the correlation. So, already we have the correlation, and this problem is pertaining to the cylindrical column 100 millimeter of diameter. So, straight away we can use those correlation which we had discussed before and substitute the value. Now, for the dynamic hold up, as you know, this u z and u v infinity is there, it is related to the Reynolds number. So, first we have to calculate the Reynolds number here, so that we can get this value. So, Reynolds number, when we substitute the particle diameter and the terminal velocity which is given, and gas density, viscosity, these are the standard, though it is I believe not given here, but these are the standard one at room temperature. One can have it because this is we can assume at room temperature all these things. So, glass material is given, so naturally it would be at room temperature. So, room temperature value of the gas density and viscosity is this, one can take. So, that gives you the Reynolds number value about 77.2. So, now we can calculate the C1, which is again fine density, then diameter of the fines, particle diameter, void fraction. So, that is how we have put it, the fine density, fine diameter, and then the other value we have put it in this one. So, that gives you 449.8. Similarly, we have calculated C2, that is a particle diameter. I think here it should be a particle diameter which is given 4.65. C3 similarly can be calculated using this. So, Reynolds number we already got. So, 6.5 and that is Reynolds number. So, you get C3, C4 of course given, uz u infinity into 1 plus. So, uz the linear particle gas velocity, you can calculate from this formula. So, you multiplied with u infinity, and that is how it has been done. So, it comes to 0.28, and the mass velocity of the gas is given by this formula, where u g is the superficial gas velocity, which is given, or rho g is the gas density divided by the cross sectional area of the apparatus. So, that is going to give you the mass flow rate, mass velocity. So, that is comes to this, and the mass fraction of fines, once you know Gg, Gk you already know because it is given, the rate is here, fines rate. So, you can, one can calculate the mass fraction which is of this. Now, all the values are known, we have calculated, we can just substitute it into the equation. Here, as you know, these both are same, and then you multiply it. So, that is how it is being calculated, this number first. So, 0.5 it is a velocity divided by, it should be the void fraction which is given 0.35. So, this stage would be a 0.35 minus of course your this uz velocity which we have calculated divided by the kappa, and so you get this value this much. Now, it is simply substituting all C1, C2, C3 and this thing into the equation. So, one can get the value of h d y kappa, kappa value is known. So, h d so this comes to this one. So, kappa is this. So, dynamic hold up is about 0.69, 0.69, and in terms of h d y rho k, which sometime it is represented. So, you divide by the density, it comes to this. So, this is your dynamic void fraction of the fines, and similarly for the static one, it is the static one. We C5 C6 is given, we are taking for the glass. This is our system. So, these are the values for this, and these all are known or we have calculated it. So, it is much easier now. So, C5 C6 given. So, this is substituting the appropriate value into your static holder formula, it gives 3.91 into 10 to the power minus 10. Now, if you look at the value of static hold up and dynamic hold up, you would say certainly that dynamic hold up is much higher than the static hold up in this case. But remember as I pointed out before, and the way this formula have been developed, it is assumed that uniform gas flow is coming out from the bottom. So, everywhere is a uniform gas flow. So, there is very less chance of the fine to deposit between the particle when you are doing that sort of experiment in the lab. However, in actual blast furnace situation is very different. It is a maldistribution, only from the side the injection of the gas and fine is happening, not from the bottom. So, it is not distributed uniformly across the cross section, and that is where it gives this sort of a hold up. So, it is a big maldistribution of the gas and fines, and one would not, in fact, it has been observed the static hold up in that condition is higher than the dynamic hold up. So, one has to be very careful in interpreting the data and using it. So, we have talked almost all part of the blast furnace except the hearth region and cohesive zone. So, now I would like to touch upon a little bit about the cohesive zone. So, this is about the cohesive zone, which is between the upper part and lower part in the middle. So, it has alternate layer of fused iron ore and coke. Those you might have not remembered, this is your cohesive zone which we said. So, it is and above this is the stack region and below this is the dropping zone. So, it is sitting in between that, and here temperature is about 1100 or 1050 like this, and it is to 1300 1250 or like that here. So, it started fusing or melting started here at this upper boundary of the cohesive zone and lower boundary of the cohesive zone, the melting is completed. So, all liquid is there. So, really this zone is like a fused zone, and that is what we are saying. So, it has a alternate layer of fused iron ore and coke because coke at that temperature is still solid. So, coke gives the required permeability to the gases to pass through this region. So, from this region there is only coke which can let the gas pass up, otherwise if coke does not coke also become like a fluid mass, gas cannot pass. So, then probably one has to stop the operation. So, coke is playing a very important part in the cohesive zone, which is allowing the gases to pass through. So, highest resistance to gas is offered by this zone, because here through the charge through the iron ore hardly any gas will pass. So, naturally whatever gas is passing through is through the coke material. So, there would be a highest resistance to the gas in this zone, and therefore, it is always required that this zone should form at higher temperature. So, it can come down and should be as thin as possible, so that the resistance to gas can be minimized and thus the pressure drop. So, these are the very important thing, and the thing also dictate the quality of the raw material and especially the high temperature properties of the feeding material. So, it is quite difficult to predict the pressure drop across this region in a reasonable way using first principle. So, due to this there have been many problems and it is not that easy. So, many experiment has been done, and based on some experimental work. So, when experiment we are talking here, it is mostly the hot experiment which have been done at that temperature between, let us say 1000 to 1300 or 1400, and sometime under the pressure because it is a burden is there at the top, which is putting a pressure on the cohesive zone. So, under those sort of condition experiment have been performed, and based on that some relation was proposed. So, based on experimental result, the pressure drop in cohesive zone can be given as by this formula. So, this is the pressure drop K G. So, G is the mass velocity of gas, rho G is the density of the gas, and mu is the viscosity of the gas, and L is the sort of the cohesive zone thickness, and K is the flow resistance coefficient, which has to be determined, and it is related to the shrinkage degree of shrinkage, because in the cohesive zone it is getting melted. So, iron ore and other material shrinks in that way. So, flow resistance is related to K naught 10 to the power 2.6 S R. So, where K naught is the flow resistance coefficient before shrinkage. So, that is when there is no shrinkage. So, one can assume like a normal bed, and S R is the degree of shrinkage. So, this S R is the degree of shrinkage. So, these are experimentally determined for different types of charge and things, and one can get the value of this. Most of the units in CGS. So, it is found that these parameters are obtained experimentally, and K naught may be taken 3.5 for most of the cases. So, based on this, one can get some approximate idea about the pressure drop in the cohesive zone. There is not much other work is done in that, mostly experimental one. So, we are really lacking in the work in terms of fused peg bed. So, based on this, there is one example. So, calculate the pressure drop across the cohesive zone having 0.5 meter thickness and shrinkage is 0.31. The gas density and viscosity may be taken as 5 into 10 to the power minus 4 gram per centimeter cube and 4 into 10 to the power minus 4 gram per centimeter second. Also calculate the pressure drop for the normal condition of the bed. Gas velocity may be taken as 1.0 meter per second. Average particle diameter is 3 centimeter. Normal void fraction is 0.5. So, normal void fraction is 0.5. Okay. So, now if we use the that formula which we just now discussed. So, first I think we have to find out the flow resistance coefficient using this. So, shrinkage is given and cannot we can take this. So, essentially this gives to this value, and the mass velocity of the gas and come per second can be given by this, which comes to this. So, which is the gas velocity in CGS, and that the thickness of the cohesive zone or the bed. So, now we have almost all the values here. So, we substitute these values into this formula. So, essentially what we get 5.3 into 10 to the power 5 gram weight per centimeter square. I think we have to look at this unit. For normal bed, we use the normal Argan equation, which is given by this, which you are quite familiar with it, and void fraction is given 0.5 in that normal condition, and all other things anyway is given. So, if you just put those values, viscosity, gas velocity, diameter 3 centimeter, void fraction 0.5, gas density, velocity. So, you get and the delta L is 50. So, you get the pressure drop 650 Joule per centimeter square. So, you can see there is a big difference, very high pressure drop is there, though the unit is a little problem, but still if we see it would be the same unit, but the factor is very high. So, pressure drop in fused zone or in the cohesive zone is very high than in the normal condition. So, that is why cohesive zone is very important.